Please hold on a second. I'm starting the screen. I'm sharing the screen. Okay, here we go. Okay. Yes, regarding that, the simulation, Monday I'll let you know. Okay, let us check if possible in the afternoon we can look into the simulation results. Um, I'll give the link, the same link. You can join and you can show the simulation. Timings I'll let you know. I'll share it through WhatsApp. Okay, the timings. Okay, here we go. Okay, so so now we'll discuss the next part of the chapter, that is sequential circuits. Okay. Yes. Okay. Next part of the so there is a sequential circuit. In that we are going to discuss what is known as to start with, of course, registers and counters, which are constructed using flip flops. Okay. Okay. Yes, I'm referring the Morris Mono textbook for this because I don't have the copy of Yarbrough textbook. Okay, so Monday I'll share any the pages of Yarbrough. Okay, so because from Yarbrough I have only till flip flops. Okay, so that's why I'll share the pages on Monday. I didn't get the textbook to home, so I'll share it on Monday. So meantime we'll start discussing in the is it here about sorry, Morris Money textbook. Of course, both are equally good, no doubt. But the thing is, some concepts may be different in some of the textbooks. Okay, so that's better to look it up. Of course, as I said in the last class, there are hundreds of books. You can't refer all of them. These two are one of the standard reference book in most of the universities and colleges. They refer these books, Morris Mono and Yarbrough. And there's one more book, of course. Again, just to limit the number of textbooks, I'm not referring that, but I can share the textbook. I got a copy of it. I'll share it through I'll share it in the group. Okay. Here we go. What is a register? Register is a. Hold on a second. Somebody's on the line. Okay. Register is a group of binary cells suitable for holding binary information. A group of flip-flops constitutes a register. That is, one flip-flop, let us say for example D flip-flop, okay, D flip-flop can store one bit of data. Okay, so this is a clocked flip-flop. Okay, so this is positive logic or just a second. Okay, yeah. So this is the what is known as positive clock pulse triggered flip-flops. I'll show you that in this Airport textbook. In this logic diagrams, according to the IEEE standard is shown. Okay, not all of these are shown in the Morse model. Okay, so we can see different logic symbols of different flip-flops, starting from SR latch, gated SR latch. What is the meaning of gated is this word you may not find in all the literature, that's textbooks. If there is enable input, then we can call it as a gated SR. Why it is gated? Because as the name suggests, gated means control. We are controlling the operation of the latches using enable input. In the absence of enable input, we don't have any control except through input. So we have to control the operation using input. In this case, not only in the input, enable also gives additional control. Gated delatch in the absence of clock pulse, of course. Okay, clock pulse will make it a flip flop. So this symbol, that triangle symbol is for the positive edge triggered flip-flops. Okay, because we have understood what is the difference between positive clock pulse and negative clock pulse. In the positive clock pulse, okay, the rising edge comes first. In the negative clock pulse, the falling edge comes first. Okay, so this is the basic difference between positive logic and the negative logic. Okay, fine. Here we go. Next is this is the JK flip flop, but you can observe this, this uh, circle here. That is nothing but a negative edge triggered JK flip flop. Negative edge triggered, it is a negative clock pulse. So the falling edge comes first. Okay, this is pulse triggered. I'll zoom it in a little because the image is not really that clear. Okay. Okay, yeah. So next is the pulse triggered D flip flop. Pulse triggered means the as long as the clock pulse is high, the flip flop changes its state as and when input D changes the state. Next is data lockout D flip flop. Okay, in this data lockout D flip flop, the symbol is it looks similar to D flip flop. Okay, but the only thing here is that. The data is protected. I mean, data is locked out. It is latched. Okay, so it's kind of a latched flip flop, something like that. Okay, of course we don't have any explicit discussion of lockout. So that's why I'm not going into detail of this lockout flip flops. Okay, so a group of flip flops forms a what is known as registers. Okay, so one flip flop can store one bit of data. Let's say we want to store this will store, for example, if D is 1, Q will be 1. If D is 0, Q will be 0. Let's say I want to store 2 bits of data. So then we can go for one more flip flop next to this. This is again a D flip flop, of course. Okay, it doesn't usually happen that one is JK flip flop, other is D flip flop. For example, the first flip flop is, let's say, D flip flop. Second one, if it is a JK, what is the input for K? It cannot be complement of the previous flip flop. Not possible. Okay, this is not possible. So usually we go for a similar type of flip flops. Okay, so this arrangement now can store 2 bits of data. N bit of data storage, we have to go for N flip flops arranged next to each other. Okay, so it can store N bits of data. Okay, yeah. So that is the for N bit register is explained in this text. Let us look into the diagram where, okay, here it is. This is a 4-bit register. 4-bit register. Okay. So what we can see here is, by the way, what kind of flip flop it is? It is an, according to this this textbook standard. According to this IEEE standard logic symbol representation, this is the type of pulse triggered, no, not a pulse triggered, sorry. In the absence of the triangle, it is a pulse triggered. So what we have in this document, it is a clocked flip flop. This is positive edge triggered flip flops. It's a positive edge triggered flip flop. That is, rising edge comes first. If there is a bubble, it would have been a negatively edge triggered flip flop. That is, falling edge comes first. Okay, here we go. Okay, so the data, the input for the flip flop is given through I1, I2, I3, I4. You can look at the convention. I1 could have been here, possible. So I1 represents LSB because we are providing 4-bit of data. I4 represents MSB. We are providing the data. For example, let's say the data input is 0010, for example. Okay. So what happens is, on the application of clock pulse, on the raising edge of a clock pulse, all these inputs are provided to flip flop, and the output of the this 4-bit register becomes 0010. Very simple. Okay. Yes. What kind of input is this? In the laboratory, ADC laboratory, I think you have an experiment where there are 4 ways of providing the input to the register. One is serial input, serial output, shift registers, of course. This we'll discuss. Shift register we'll discuss next. Next type of possible combination is serial input, parallel output. I don't know whether any of you done this experiment. So parallel input, serial output, PISO. And the next possibility is what is known as parallel input, parallel output. Okay, fine. What is this? Oh, we'll quickly go through this, so that we understand the circuit what we are discussing. Okay, so let's say there are four-bit register. This is the four-bit register where we apply the input as I1, I2, I3, I4, I4. Okay, so it has four outputs. Let us say you can give any name: O1, O2 output, O for output, O3, O4. If we can provide the data serially through one pin, let us say I1 for example, okay, 4-bit of data. Let us say the input is 0010. Okay, we are providing the data serially. The data will be shifted from one flip flop to another flip flop. So there are four flip flops, four D flip flops, preferable. Okay, usually D is preferred. Okay, so what happens is that we'll provide the data through one input and we shift the data from one flip flop to another flip flop. Okay, and then the register acts as a shift register. Register acts as a shift register, and we'll get the output one at a time possible. That is through O4 we can obtain one at a time. Then we can call such kind of a register as serial input, serial output register. That means we are providing the data serially. That is, serially means one after the other, bit after bit. Data are shifted from one flip flop to another flip flop. We'll obtain the output serially. We can call it as a serial input, serial output shift register. The other possibility is, let us say we have provided 4-bit of data through I1, I4, whatever it is. Okay, and we can obtain the read the data all at a time. For example, input given is 0010, output obtained is 0010. We can call it as serial input, parallel output, shift register. Parallel means we are able to observe the output, all the bits of the output at a same time. We can call it as a serial input, parallel output, shift register. Next, parallel input, serial output. We are providing the data parallelly through all the inputs, 4-bit register, 4 inputs, 0010. We can obtain the data. We'll first load the data. Okay, when we load the data, flip flop stores the data as 0010, and after shifting from one flip flop to another flip flop, okay, we can read the data from one output. We call it as parallel input, serial output register. The other possibility is we provide all the inputs at the same time, 0010, and we can read the data all at the same time through all the outputs of the register. We call it as parallel input, parallel output register. Okay, so these are the basic 4 types. So what we have in this situation is we are providing the data parallelly through inputs I1, I2, I3, I4, and these flip flops stores the data. But the register what we have is not a shift register way, because there is no connection between internal connection between these flip flops. Like output of one flip flop is fed as input to the next flip flop. No, we don't have such arrangement. This is not a shift register. It's just a normal register where it can store 4-bit of data. So only possibility out of these four options, only possibility what we can achieve in this case is only parallel input, parallel output operation. Okay, that means we can provide the data parallelly. That's the only possibility, because it does not shift the data from one flip flop to another flip flop. We can read the data all 4 at a time, and then this is a simple example of a parallel input, parallel output shift register. Not shift register, sorry, normal register. Is okay, but this will trigger only on the application of the clock pulse. Okay, okay, register with a parallel load. Okay, let us understand this now. Now register, we'll try to fit it to the page, so you may not okay, something like this. Okay, this is a 4-bit register with a parallel load. Okay, what is the meaning of a parallel load? Now what happens, there is we are providing the, see, in the earlier case we used we have a D flip flop. Let us quickly look into this. It's a D flip flop, simple D flip flop. We are providing the data all at a time. We can obtain the data all at a time. Okay, So there is no control over the operation. I mean, except clock pulse. Now we have parallel load register with a parallel load. Okay, so this in this case, transfer of new information into register is referred to as loading the register. That is providing the data to the register. Okay, so for the parallel load register, um, just a second. Okay, so if all the bits of the registers are loaded simultaneously with a single clock pulse, we say that the loading is done parallel. This we just now we understood because we discussed four types of operating the shift registers. One of them is parallel input, parallel output shift registers. Pulse applied to CP, that is clock input of the register, will load all the four inputs parallelly. Okay, so we are loading the data parallelly. Let us jump to the circuit diagram. Okay. Here we go. This is the, I'll try to fit it because it looks very okay. In this case, what we are making use of is a SR flip flop. Okay, guys, what kind of flip flop it is, by the way? Again, if you look into this IEEE standard logic symbols, this is SR, flip flop, not the latch. Okay, in the latch we don't have a clock pulse. Okay, so what we have here is a flip flop, SR flip flop. Okay, positive clock pulse triggered or positive edge triggered flip flops. Okay, now uh, instead of okay here, since it is a parallel load register, we have to make use of both the input. Okay, that is both S input and as well as there's one more thing we have to observe here. Okay, in this let me zoom in. Okay, so that I'll go to the last flip flop so that we can okay, let's observe the inputs for the flip flop. Okay, what are the inputs applied to the flip flop? One is the clock pulse. Obviously, this is nothing but a normal, sequential circuit. That is what you call, synchronous clock pulse, synchronization signals. Okay, so this clock pulse will go to the, this um, clock pulse. So no, not get it is complemented and it is applied. Okay, so even if it's complemented, we get back the complemented signal. In that, the flip flop will trigger at a positive edge of a clock pulse. That's simple. Even after complementing, we get something like this. In this case also, it will trigger only on the positive edge. Very simple. Okay. Why it is complemented, I'll tell you. Why this is why it is complemented. Why we could have straight away applied to the flip flop. That's also possible. Okay. Let's observe the next one. It is a clear input. Okay. Clear input uses a triangle symbol. In one of the earlier class, we have discussed a concept called as buffer. If you remember, buffers. What is buffers, guys? Buffers is basically there are two types, multiple types of buffers. One type of buffer is a complement buffer where it will complement the data. Not only that, it will amplify the current. In this type of buffer, it will only amplify the current, but it will not complement. Okay, it's only amplify the current. What is the purpose of this buffer? Okay, let us understand this. The connection of the buffer. These buffers, this clear input is connected to a. Of course, it is not specified what is this input. This is the input called as clear input, CLR. CLR input of a flip flop. What is the CLR, guys? In the last class, if you remember, we discussed clock pulse with two additional input. They are called as preset and clear, represented as PR and CLR. Okay, preset and clear. What is the function of these two? The inputs. Preset, if 0, it will force Q to be set to 1. If clear is 0, it will force Q to be set to 0. If both are 1 1, flip flop output depends on the input, whether it's a D flip flop or a T flip flop or whatever it is. If both are 0 0, then output is invalid. Output becomes invalid. Okay. So this clear input is being used to clear the content of the flip flop. Let us say I want to start with all the output 0. There are 4 flip flops, 4-bit shift register. I want all the outputs of the flip flop to be 0. Then this signal should be 1. Why? Because it's the active low signal. Active low signal, when we apply 1 to clear signal, all the output of the flip flop becomes 0. All the output of the flip flop becomes 0. Okay. Sorry, not 1. Sorry, guys. I'm sorry. I made a mistake. It is not 1. It should be 0. Okay. If clear input is 0, all the output of the flip flop becomes 0. Whereas if the clear input is 1, output of the flip-flop depends on the input. That's how it is. Okay, yeah. So we'll discuss this, the parallel shift register now. Before that, let's just a second. Yes, just give me a second, because there is various types of the sequential circuit discussion, but this is flip flops. I think it is given in this document. Okay, give me a second. Master slave jacket flip flop. Meta stability. No, it is not here. Let's trigger flip flop we discussed. Okay, sequential circuits. Simple affair. Okay, sequential circuit. Okay, I'm looking for one circuit, where sequential JK flip flop. Okay, state reduction assignment. Okay, I think we should discuss some. Okay, these are the the logic equation realization using the okay. Let's okay. I'll go back to this diagram. Let's just give me a minute and okay, actually there are a lot of state reduction concept. We'll not discuss that. Okay, so a lot of details into that. Okay. Clock sequential circuit example. Okay, please now before we continue with that parallel register. Okay, so we'll take one simple example of a sequential circuit. Uh, okay, x and y. Okay, state table. Okay, yeah, that's okay. Now look at analyze this circuit, guys. Because explicitly the clock to the sequential circuit. These are the direct layer. Okay, something like this. Direct layers signal. Okay, yeah. Yes, this observe this circuit. This is an example of a simple sequential circuit. Okay, what does this sequential circuit as, guys? This as I'll try to fit it to the page. Okay, it's a D flip flop basically. Okay, so this is a clocked D flip flop. Let's observe this circuit diagram. Let us not worry about the operation. Okay, so I'm not interested in this operation now. What I'm trying to say is, uh, one possibility is we can store the data into the flip flop by providing input to the flip flop. Okay, so for example, if D input is 1, the output of D, D, the first D flip flop, it becomes 1. Okay, and for the second flip flop, the input is 0, output becomes 0. Very simple. Okay, now what happens is that we want to build a sequential circuit for which the basic is the combination circuit and the latches. Okay, yes, I'm trying to search for that diagram. Just it's not no, not here. Yes, this one. Yes, here it is. This should be okay. Okay, block diagram of a sequential circuit. How does the sequential circuit works? But they given the diagram after the what do you call that? What is the page number? It's just give me a 239. Okay, here we go. That should be good enough to understand. See, in case straight away here we have the sequential circuit. Yes, here it is. What about this one? Okay, okay. Yes, before we come to this, 239 is the page number of sequential. So yeah, here it is. Okay, fine. Let's check out this. Let's in this case, how do we convert a latches into there is asynchronous circuit into what is known as sequential circuit. Yes, in the beginning we discussed two types of circuits. What is known as a combinational circuit. What is an example of a combination circuit, guys? For example, full adder. demultiplexer, multiplexers, decoder, encoder. All this becomes example of a combination circuit. Next comes what is known as sequential circuit. Okay, in sequential circuit there are two types basically. One is known as synchronous sequential circuit, synchronous circuit. In another type of circuit is what is known as asynchronous sequential circuit. Asynchronous sequential circuit. Now what happens is that combination circuit output depends only on the input. But any number of output depends only on the inputs. In synchronous sequential circuit and asynchronous sequential circuit, basic requirement is that there should be what is known as a feedback. There should be what is known as a feedback. The feedback can be a simple feedback like this, straight away connect output to input. That is a feedback, no problem. Okay. The other possibility of a feedback is that, please hold on a second. Yeah. Other possibility is that this feedback network will have additional circuitry, for example, additional combinational circuitry. In fact, this is a combination circuit, sequential circuit as a combination circuit with a feedback. The feedback can consist of additional combination circuit that may be clocked, or may not be clocked. That means clock means it is applied with a clock, and the output of the combination circuit is given as input to the sequential the feedback network. The output of the feedback network is given as input to the combination circuit. In this case, if the circuit is clocked, we can call it as a synchronous sequential circuit. If it is not clocked, then we can call it as a asynchronous sequential circuit. Okay, fine. The example for asynchronous sequential circuits are latches. Latches, why? Because there are feedback, but it is not clocked. Example for synchronous sequential circuits are registers, where there is not only the feedback, there is also what is known as a clock pulse applied. Okay, so this concept is explained in this diagram. Yeah, here it is. Okay, observe this. We have basically flip-flops, JK flip-flops. The output of the, observe this output case, A and A dash, that is Q and Q dash of the flip-flops are given as feedback to the combination circuit. Okay, this is a combination circuit, something like this. Feedback to the combination circuit, something like this. Okay, and the output of this combination circuit, which is available at the feedback, is given as a input to the sequential circuit. So just a second, hold on. Hello, hello. Okay, sorry, one first student, for meeting details of action point. Okay, yes, okay, where I was, yeah, here it is. Okay, so the output of the combination circuit are given as input to the another combination circuit, or it can be sequential circuit. In our case, this network, what we have in this example, is a sequential circuit. This can be sequential, or it can be combination circuit. Okay, so thereby what happens now is, observe this feedback network. This combination circuit as a external input. That means along with the feedback, it also has a external input. It can generate output. That means this feedback network can provide its own output. This network can provide its own output. It can have its own input. Along with the feedback, it can have input, as well as it can provide the output possible. All these examples we'll see. Okay, and this part of the output, see, there are multiple outputs from this feedback network. One is this external outputs, and these outputs from this feedback network, that's combination network, is given as an input to the sequential circuit. Together we can call it as a sequential circuit. Why? Because this part is a combination circuit. Okay, this is not clocked. Observe this, guys. This is not clocked, whereas This part of the circuit is clocked sequential circuit with a feedback. Together we can call it as a synchronous sequential circuit. Okay. So one such sequential circuit is going to we are going to discuss now. Okay. So this is the basics. So after this is okay. In the sequential circuit, if you observe, okay. So let us see the this example. With the I'll show you the function table so that we'll understand. There's a design procedure for this with the state diagram. I'm not discussing state diagram here anyway because that itself is a separate okay, concept design. Okay, is it necessary to okay? Mm, oh, please don't worry about this, because there's a separate design procedure for that we have to discuss. Um, with respect to state diagram, those diagrams are given with respect to state diagrams. Okay, right. Here we go. Okay, now here we are. With that concept, we have this situation where here we have parallel load. So we have a common input called as a clear input applied through using a buffer. This, if it is 0, it will make all the outputs equal to 0. It will make all the outputs equal to 0. Okay. Whereas if it is 1, output depends on the input and the clock pulse, of course. Okay. So we are applying the clock pulse to this input through a inverter buffer. So this will make sure that uh, any number it can apply clock pulse to any number of input without reduction in the current. Okay, because it has to drive so many gates. So if multiple flip flops are connected, the current will the current will diminish. So and hence to strengthen the current, we are using the buffers. Okay, otherwise we could have directly applied the clock pulse. One or two flip flops, okay. Multiple flip flops, we have to go for a buffer. Look at the load input, guys. Okay, load input is applied through another buffer. Why? Because this load has to drive load signal. What is a load signal? It is nothing but a logical signal. Okay, so we can set it to high or we can set it to low depending on the requirement. Okay, so since it has to drive multiple gates, here how many gates? 4, 5, 6, 8 gates it has to drive, and hence it is connected through a what is known as a buffer. The buffer is a basically current amplifying device. It will amplify the current. Okay, fine. Here we go. Okay. So now observe this, the parallel, 4-bit register with parallel load. So we are applying the input I1, I2, I3, I4 through the AND gates, okay, and also through the NOT gate, okay. So for example, we'll take one simple example, okay. Assume that parallel load input is 1, for example, okay. If load input is 1, the input for these gates are 1. Input for these gates are 1. Wherever the load is connected, input for these gates are 1. Okay. Now output of these gates depends on the data input. I1, I2, I3 forms the data input. We'll take one example now. Let us say the input is, same example we'll take 0, 0, 1, 0, for example. You can take any example. Okay. So observe this, these inputs are provided to these input, the AND gates. So 0 complement of that is 1. This is 0, the complement of that is 1. Here it is 1, the complement of which it becomes 0. And here it is 0, that means this input is 0 and this input is 1 because it is complemented. Okay. What is output of this AND gate, guys? This is 0, this is 1, 0, 1, 1, 0, 0, 1. Okay, here we go. Okay, look at the input for the SR flip flop. Okay, SR flip flop inputs are 0, 1, 0, 1, 1, 0, 0, 1. Okay, what is the output of SR flip flop? Okay, so SR flip flop generally, when you say SR, there are two types of SR flip flop. We should not forget this. In this the logic symbol it is shown here. Okay, just a second. Okay, in this logic symbols SR flip flop, there are two types of flip flops. One is the normal SR flip flop and gated SR latch, SR latch or SR flip flop. Okay, so in this case, depending on whether it is made of NOT gate or NAND gate, we can have SR flip flop or what is known as S dash R dash flip flop. Okay, so based on this difference, in this case, okay, so what should be the I think is it erased now? Oh, no problem. Okay. Oh, say all erased. Okay. Okay, I have to write again. Yes, one. Let me write, in one simple 0010. Okay, mistakenly I erased everything. Okay, so okay. Anyway, no problem. This is zero. This becomes one. Sorry, this is zero. Zero. This will be one. So this will be zero. One. This is one. Okay. This is one. One. This input is one. This becomes zero. If this is zero, this input is 1 and this input is that is 0 and this is 1. Very simple. Okay, fine. Now what is output? Output is, for an SR flip flop, we know that if S is equal to 0, R is equal to 1, then Q is equal to 1, Q dash is equal to 0. This is R is equal to 1. This is R is equal to 1. Okay, accordingly let us write the output. Okay, S is equal to 0, Q is 1. Because if you observe this flip flop, in fact Q dash is not shown. Why? It's not used until and unless we want a feedback. Yes, something like what we see in the sequential circuit, what we discussed now. There was a feedback. Here there's no feedback, so it's not necessary. So Q dash is not at all mentioned. Okay, so Q is 1. In this case, again Q is 1. Here it is Q is 0. Here it is Q is 1. Okay, fine. So what is the input we have provided, guys? 0010. What is the data loaded in the register? 1101. 110. Why it is 1101? Because we are using SR latch. In which case, if S is equal to 0, Q becomes 1. If S is equal to 1 and R is equal to 0, Q becomes 0. That's how it is. Okay. Now observe this. What if the load is 0? What if the load condition is 0? Let me erase this also. So let me write again. If load is 0, all the inputs of this AND gate becomes 0. All the input of this AND gate becomes 0. Okay. So in fact, load is connected to all the gates, and hence output of all the gate becomes 0. That means SR input for this parallel register is 0000 with all inputs as 0 for a shift register. What should be the output, guys? What is the output? When the inputs are 00, when the inputs are 00, there is no change in the output. No change in the output. No change in the output. Okay, that means if load is 0, even if you change the input, even if you provide any input, to the register, it will not be loaded. We can say that this will not be loaded to the register. Why? Because load is 0. If load is 1, then only the data input will be loaded to the shift register. Okay, so this is the application of what is known as a load input. That's why it is called as a parallel load. Parallel load means all the 4 bit of data can be loaded at once with the help of a additional input called as load input with the input of 1. That's okay. So this is what is called as parallel input. Somebody is on the line. Okay. Okay, that is called as a 4-bit parallel shift register. Very simple. Okay, so what we have to understand here is, though these are the sequential circuit, we are using additional combinational circuit to form a complete sequential circuit. Okay, synchronous sequential circuits. That is a clear input we understood. Okay, so one more example. Okay, using D flip flop. Okay, so this is this is an example of a sequential circuit where there's a feedback. Okay, something like what we discussed just now. Okay, that is this diagram. I'll show you it. This diagram what we discussed just now, which has a feedback. Yeah, here is it. 239 page number. Okay, here we have a flip flops which is provided with the clock pulse. There is a feedback given to the combination circuit. This combination circuit has an additional input and additional output, and the output of this combination circuit is given as input to the flip flops or any circuit for that matter. Then we call it as a sequential circuit. One such example what we have now is with a D flip flop. Let us jump to that circuit now. D flip flop, parallel input, parallel register with D flip flops. Yeah, here it is, D flip flops. Okay, observe this diagram. So here we have the same situation. 4-bit register basically that is to store 4-bit of data. It has clock input. This is just another clock input. It is inverted with the buffer so that it can trigger all the flip-flops at a time, at one time, okay, depending on the edges of the clock pulse. This is a positive edge triggered flip-flops, and then so the flip-flops will change the state only during the positive edge of a clock pulse, only during the positive edge. During the negative edge, in fact, say, when once it will change the state only during this duration, only in this during this time, until occurrence of the next positive edge, it will not change its state. Very simple, okay, because it's a positive edge triggered flip-flops that we provide control using clock pulse, clock input, clock pulse. Clear input, just now we understood, clear input, what does it do? If clear is 0, all the outputs of the flip-flop become 0. That means we are flushing out all the data. Very simple. We're clearing the data, and then once the clear input is 1, output depends on the input. Okay, input of the flip-flop. Let us see how does it work now, along with the load input. Now the load input, observe this. There are 2 inverters. Okay, yeah. Earlier there was only one inverter. If you see the previous diagram, there was only one inverter. If you can see, of course, sorry, the inverter was for the input, not even for the clock pulse. Sorry, there's no inverter here. In this case, we have 2 inverters. How it is connected? Observe this. Okay. Okay. Now, the input stage of the 4-bit parallel register consists of a combination of gates in 2 stages. In the first stage, it is a 2 AND gates, and in the second stage there is a OR gate. Second stage there is a OR gate. How does it work? Observe this. Okay. Yeah. Let us say, for example, load input will take one condition. Let us say 0. Let us start with 0. Okay. Now, load input is not straight away directly applied to the gates. It is complemented first. In the first stage, when it is complemented, it becomes 1. That means these gates are applied with 1. These gates with in first stage of the gates are applied with the logic 1, and it is further complemented, it becomes 0, and that is applied to these gates 0 0 0. Okay, so let us see how the circuit circuit changes. Okay, so the gate AND gate with the input 0, obviously the output will be 0. Okay, so these AND gates outputs are 0, AND gates outputs are 0. Very simple. Okay, now the input is applied. Let us take some example, 0 0 1 0, for example. One simple example, 0 0 1 0. Okay, so this input is 0. This is where is this? This is 0. This is 1, and this is 0. This is 0. What is the output? Output of the first stage of the AND gate not only depends on the load and the input, it also depends on the previous state of the flip-flop. Okay, fine. Let us assume initially, just to just for analysis purpose, let us say initially it was 0. Just to understand, let us see how does it will affect the. Okay. Now, if it is 0, observe this. If these inputs are 0, for example, if these inputs of the AND gates are 0, AND gates are 0. Okay, what is the output of these AND gates? 0. All the first stage AND gates now as the output of 0 0, and because of 0 0, OR gate output is also 0. OR gate output is also 0. Input for the D flip flop is 0, and hence output remains 0. Output is at 0 level. Okay, fine. Now the other possibility. Okay, so let us consider the other situation where load input is given as 1, because what we discussed is for load input 0. Now load input is 1. Okay, with the load input 1, okay, this becomes 0. This stage is 0. This is 1. So that means this is 0. This is 0. This is 0, and this is 0. And the other inputs are 1. This is 1 1. This is 1. I think this is also 1. Correct. Other inputs of the AND gates, first stage AND gate is the parallel input 0 0 1 0. That means these inputs are 0. Where is it, guys? I think I made. Okay. Yes, correct. This is 0. Correct. This is 0. This is 1, and this is 0. Okay. Wherever there is a 0, output is obviously 0. It doesn't matter what is the previous output of the clock pulse. Let us take it 0, for example, just to make it simple. These outputs are 0. These outputs are 0. Okay. And look at the other AND gates, because there are some AND gate. Okay, in this case it is 0. This AND gate is 0. Here it is 0, but in this case it is 1. This output of the AND gate is 1. Okay, this is also 0. So because of this condition, the output of this OR gate is 1. That means this D input is 1. All other D flip-flop inputs are 0, 0. Output now is equal to 0, 0, 1, 0, 0, 0, 1, 0. Okay, that means we have loaded the input, parallel input to the register using load input. Okay, so if load is 1, data will be loaded to the register. If load is 0, load input is 0, the registers will retain its previous state. It will not lose the data, but it will retain its previous state if clear input is 1. Whereas if the clear input is 0, all the output will go to 0. All the output will become 0. Yes, okay. So this is how we control the operation of the register, parallel register, using what is known as a load input. Is that okay? So this is a good example of what is known as a what is sequential circuit. Okay. Okay. This the same thing is explained with respect to the clear input and the load input. You can go through this text. Okay. Okay, here there is a definition given. This type of transfer is called as a parallel load transfer because all the bits of the registers are loaded simultaneously. That's why it's known as a parallel register. This we discussed. In this example, we discussed parallel register where we can apply all the inputs at the same time. Sequential logic implementation. Okay, fine. Here we go. Because with this, I'll wind up. Just 2 minutes. Okay, here we have. This is what is known as a sequential. Of course, we already saw sequential circuit. One type of sequential circuit. There, it was given as a combination circuit. The same thing. What we saw in the page number 235 is given in the form of a block diagram. Very simple. Okay. There, the gates are given. Shown here. The block diagram is shown. Very simple. Okay. The same circuit diagram. A register with the clock pulse. The register. Okay. Because in the earlier case, 239 page, the flip-flops were shown. The inputs are shown as the register, the sequential circuit was shown as the flip-flops. Now it is shown as a group of flip-flops called as a register. Group of flip-flops called as a register. This register will have a input clock pulse, and the output of the combination circuit is given as an input to the register, and the output of register becomes input for the combination circuit. This combination circuit as an input. This combination circuit as a input to the input, and it has its own output. That means we can read the output from the register as well as we can read the output from the combination circuit. Okay, so the depending on the previous condition, the next state of the register can be determined. Okay, why? Because let's say this is one. Let us say this is a D flip flop. There is a register consists of D flip flops. So the input is one. The next state will always be one. The output of the register is also going to be one. Very simple. Okay. Depending on the flip flops used, there is sequential circuit. Okay. So there's one design example of a sequential implementation. Okay. Let us understand this. How to design a sequential circuit for a given state diagram or given condition. Okay. So let us take this example. Design the sequential circuit whose state table is listed in 758. Okay. So this is what is called as a state table, not a truth table. Why? Because state table, because here just a second. Yes, yes. Okay. Sorry. Okay. Yeah. Hold on a second. What? Yes, just a second. Just a second. Okay. So sequential circuit. Okay, sequential circuit is in state diagram. Um, State diagram. Okay, what is this state table represents? It has present input. There is present input applied to. Okay, first look at the diagram. Of course, actually we have to design this. This here it is. It has two sequential circuits, A1 and A2. The present state of this sequential circuit is represented as A1 and A2. Input is X. Okay, okay. Input is X. With this input and with the feedback, what is the next state of this A1 and A2? It is represented as next state of A1 and A2. And what is the output of the circuit? That is represented as 1. Okay. Yes, observe this this condition now. Table specifies two flip-flops, A1 and A2. It should be a flip-flop because the register consists of flip-flops. We can call it as a 2-bit register. Okay, input is X and output is Y. The next state and the output information is obtained directly from the table. Okay, fine. In case if it is present state, if it is 0 0, and if X input is also 0, okay, means what will happen is this becomes X, and this is also X, and this will be 1. Okay, and this is the output. This is also 0. Why? Because it is coming from A2, and this is also 0, which because it is coming from A2, this will be 0. That means Y is 0, and because this is 0, this input of this AND gate is 0, this is 0, 0 is fed back as input. Here it is 0 0, this is 1, 1 is fed back as input. Because of this, output is 0. Here it is 0. So next state is also 0 0. Next state is also 0 0. Okay, fine. Now similarly, in the same way, with the 0 0 condition, if X is 1, if X input is 1, what will be the condition? Observe this. Okay, so let us analyze this also. With X is equal to 1, and if the output are 0 0, output from A1 and A2 is 0 0, that means this is 0, this is 1, so this 1 complement becomes 0. Okay, so this output obviously becomes 0. This is 0 and this is 1. What is 0 and 1? Means XOR gate output is 1. Okay, that means A2 is equal to 1. A2 is equal to 1. You can see that here. A2 is equal to 1, whereas A1 is still 0. A1 is still 0. Okay, next state is also 0, and output is also 0 because output is the Y is the output of this AND gate. It is equal to 0. It is equal to 0. Okay, like this, we can analyze for all the possible input conditions 0 0 0 0 1. Okay, 1 0 and 1 1. Okay, each state with the input of 0 1, because there is only one input, 0 1 0 1 0 1 and 0 1. For all these input combinations, what is the next state of flip-flops, that is A1 and A2, and for this condition, what is the output of the circuit, that is Y. Accordingly, if you write in terms of equation, okay, mathematical equation, for A1 of t plus 1, that is the next state, can be written as only these two guys, observe this. A1 of T1 is 1, next state is 1 only for these two conditions, where it corresponds to, let's observe this, it's a 3 variable function, okay, there is A1, A2 and X, 3 variables, 0 0 0, similarly 0 0 1 up to 1 1 1, decimal values 0 1 2 3 up to 7. Okay, with this combination, 1 0 0 corresponds to 4, and where is this? 1 1 0 corresponds to 6. So we can write expression wise, we can write A1 of t as A1 of t plus 1 as summation of min terms. Basically, it is a min terms 4 and 6. Very simple. Okay. What about A2 is similarly? A2 of t plus 1 is 1 for 1, 2, and this is 5 and 6. 1, 2, 5 and 6. Okay. A2 of t plus 1 is 1, 2, 5 and 6. Okay. Okay, 1 2 5 and 6, and next is y. Y is a function of 3 variables, a1 a2 and x, so it is nothing but equal to these 3. Okay, so it is 1 for these 3 conditions. There is 0 1 1, that is 3, and 1 1 1, that is 7. 3 and 7, very simple. Okay, now using this we have to design the sequential circuit. Okay, how do we design the sequential circuit? Guys, observe this. A1 and A2. There is 3 and 7. Okay, so 3 and 7 is somewhere here. 3 and 7. I think it's given in the, just a second. In case if it is given here, we can is XOR gate. Okay, straight away. Min terms, or 4 variables. Okay, for variables. Okay, the functions how to design is shown here. Okay, logical function. Okay, fine. Okay, the steps are not shown. Okay, that's K-map. We can design using simplify using K-map. Okay, so K-map is a 3 variable function now. We have to design for how many what is the type? It's last minute is already type. Okay, for y, first we have to design for y. Okay, this is a1, a2 and x. Okay, a2 and x. Okay, so y is for 1 for 3, 0, 1, 2, 3 and 7. This is 7. Group this, we get the expression as a2 and x, a2 and x. So it becomes a AND operation of a2 and x. Oh, sorry. Okay. So similarly, A1. This, take one more, K-map. Simplify for A1. Similarly, A2. We get these two gates. After simplification, the author has shown the equation. Okay. After simplification, the author has shown is like this. Okay. So A1 of t plus 1 next state A1 x dash. A2 of t plus 1 XOR operation of A2 and x. XOR operation of A2 and x. This is A2 and this is x. Okay, and similarly y is A2 and x. That's all. Okay, so that's how we are going to implement a combination circuit. Sorry, we are going to implement a Boolean expressions using the sequential circuit. Yes, more on this we'll discuss in the coming classes. Okay, let me. It's already time. Add a few disturbances. Okay, anyway, thank you guys. Thanks for joining. Okay, see you in the next class. Bye.
Thank you, sir.
Okay, good day.
Thank you.
Happy weekend.
Thank you, sir.
Thank you, sir.